last time we were talking about thermodynamics, and we were talking a lot about entropy and stuff, and having microstates where not partitions, but particles, right, can be in certain places and stuff like that, and those are called microstates. It can be over on the one side of a flask or on the other side. Both can be on one side of the flask, or both can be on the other side of the flask, and those are all called microstates. And so what that means for us then is that we can use statistics, right? We can use statistics to figure out what the probability is then of a particle being in, or multiple particles being in certain positions on a in a thermodynamic scale or thermodynamic sense. There we go, manner, right? So um, thermodynamics looks at the bulk properties of substances, the big picture, but we have seen what happens on the molecular scale, right? So how do they relate? Well, we use statistics or statistical thermodynamics to figure that out. And like I just said a second ago, what is a microstate? It is a single possible arrangement of a position and the kinetic energy of molecules, right? And so uh, it may sound like there's going to be a lot of math here, but there's not a lot of math. Not as much as we had in the last couple chapters, right? So remember I was talking about Boltzmann? I think his name was Ludwig von Boltzmann. He came up with this very simple equation right here that actually helps you figure out the entropy of a system based on the microstates, and uh, uh, and uh, and this K right here is actually the Boltzmann constant. Okay, the Boltzmann constant, which can be looked up if you need to look it up, right? It's one of those things that it's just like the ideal gas constant and all those other constants. It never changes, right? But he came up with this very simple equation where if you do the Boltzmann constant and the natural log of the microstates, you actually get S, which is the entropy of the equation of the system, right? The entropy of the system. So it's super simple, and it's so simple that when you go to, so I went to visit his grave when I was in Europe, and his grave site and his tombstone actually, most people have, loving father or something like that, survived by or something, you know. His tombstone actually has that on there, right? So he was very proud of that equation. Good old Boltzmann. I'm pretty sure his name was Ludwig Boltzmann, but is that Ludwig von Beethoven too? I don't remember. Anyway, I may be confusing my Ludwigs, but wasn't one of Bowser's kids on Super Mario Brothers also named Ludwig? I can't remember now. Sorry, off topic. So your first question for today, right, is this, right? What is a microstate? Which I just said in the last slide, but let's see if we can get it here, right? It describes the macroscopic view, system characterized, for example, the pressure and temperature of of a sample gas, right? It is a single possible arrangement of a position and the kinetic energy of a molecule. It can be thought of as a measure of randomness in the system, or none of the above. None of the above, right? And so, okay, so anybody can guess? Can anybody guess what the answer is here? Yes, it is in fact B. Good job. Very good job, right? Because that is definitely the single possible arrangement of molecules, right? It's definitely not A. What A is actually the definition of a state function, right? So things like pressure, temperature, internal energy, entropy, enthalpy, those are all called state functions, right? Because they matter more about the state of what is going on than how you got to that state, right? So that's actually the definition of a state function. And then, of course, you already knew B is the definition of microstate. And then C, what is the definition? What is this the definition of? Can be thought of as a measure of randomness in a system. What is C? Yes, that is the definition of entropy. Exactly. That is the definition of entropy. So it's more important than ever that we understand the definitions of all these words that we're using, right? That way you can answer questions, on the exam and stuff like that. Um, since there's less math to do now, it's more about understanding what everything means, right? So you can get the change in entropy here by doing the Boltzmann equation right here with the final minus the initial, right? And we can use the quotient rule here to get this where now delta S is equal to the Boltzmann constant times the natural log of the the final microstate divided by the initial microstate, right? So the microstate it was at the beginning divided by, sorry, the microstate at the end divided by what it was at the very beginning, right? So this is how you get an entropy. You can figure out what the change in entropy is. Because remember, we always have this delta, which is change in something. And so delta S means change in entropy, right? We've seen already before at the beginning of the semester, um, delta H, which is the change in enthalpy, right? But this is going to be the change in entropy, okay? So good stuff there. It's not going to be the last time we see something like that, okay? So what is the effect of volume and temperature change on a system? Well, we know that if we increase the volume, there are more positions available for the molecules, right? So if there's more volume, molecules can be all different places more, right? So this results in more microstates. So that means that there's more entropy, okay? And then if we increase the temperature, that actually also increases the kinetic energy, right? Just like normal, right? We heat something up, it increases the kinetic energy in the molecules, right? That results in a greater distribution of molecular speeds, and therefore it's going to be more. There's going to be more possible kinetic energy values, resulting in more microstates. So that also increases entropy, right? So in the end here, right, you just got to remember that increasing volume and increasing temperature increases both microstates and what else? Entropy, right? Microstates and entropy. Increasing temperature and increasing volume makes more microstates and makes more entropy. That's important to know. Okay, so what does it mean then when we have an increase in temperature and then you have like an increase in microstates when it's talking about like molecular movement, right? Well, it turns out that molecules actually exhibit several types of motion, right? And these are the three types. There's the translational, right, where the movement of the entire molecule from one place to another. That's the one that you're probably most used to, you're probably most familiar with, right? For example, you heat up a molecule and it moves from one place to another, right? But it also goes through a vibrational too, and this is periodic motion of the atoms within the molecule, right? So the thing that's important about this, especially when you get to OChem, is using with IR spectroscopy, right? FTIR spectroscopy, and so molecules, so like this molecule of water right here, right? I think it's water. Is that water? Yeah, yeah, that's got to be water, right? So there's these three vibrational modes you can have with water, and so the middle one here is called wagging, where the hydrogen of the oxygens wag back and forth, right? That's called wagging, and then this one here, right? I can't remember what that one is called, but it's the symmetrical movement of the hydrogens going up and down like this into the oxygen, right? And then this one here, I can't remember what it's called either, but it's an asymmetrical movement of the hydrogens going up and down like this into the oxygen, right? So those are the vibrational states, okay? And you'll learn way more about those states when you guys talk about FTIR in in organic chemistry. And then there's rotational, right? And rotational is literally just the movement of the molecule about an axis in a circle, right? So note that more atoms means more microstates, so more possible molecular motions, right? So these are important. You need to know these three molecular motions right here and what they mean, okay? So the number of microstates and therefore the entropy tends to increase with what? Temperature, volume, and then the number of independently moving molecules, right? And these are those molecular motions, okay? Those are those molecular motions. So your next question is this. Which of the following is not a molecular motion? Okay, which of the following is not a molecular motion? So which one of these is not a molecular motion? Answer? Yes, all of them are molecular motions. Good job, good job, good job. Means you're paying attention, right? So if we know then that entropy increases with the freedom of motion in molecules, then we can deduce that The entropy of a gas is greater than the entropy of a solid, and then is greater, sorry, entropy of a liquid, and then greater than the entropy of a solid, right? Because gases have all kinds of motion going on, don't they? Right? They're just floating around all over the place, bouncing around in all random situations. They fill up, right? Volumes of anything, right? Any kind of container, they fill up. So gases have all kinds of molecular motion, right? Because they're going all over the place. Liquids, they kind of fill their space, but they tend to just fill their space. They don't just expand, right? And so but they still have more movement than a solid does, because a solid is just, just sitting there. So there's not a lot of movement. Your tables won't work very well if there was a lot of molecular movement in a solid, right? So this is another thing you've got to know, right? The entropy of a gas is more than the entropy of a liquid, and that's more than an entropy of a solid, right? So here's the statements you got to remember. Entropy of a system increases for processes where gases form from either solids or liquids, right? So if a gas comes from a liquid, like in sublimation, right? I'm sorry, gas comes from a solid, like in sublimation, or if a gas comes from a liquid, like in evaporation, that's going to be an increase in entropy, right? Liquids or solutions from solids, right? That's like melting down ice into water. That's going to increase entropy, right? Or solutions, like you add solid salt into water and it dissolves, that's going to be an increase in entropy, right? Does that make sense? Okay. And then the number of gas molecules that increase during a chemical reaction, and we're going to talk about that now. Okay. This is a big one here. If the number of gas molecules increase during a chemical reaction, then there's going to be an increase in entropy. So take a look at this, right? Oh, God, I thought I made this bigger so I could read it better, right? So this is just an example of the first couple ones, right? We have a very solid, rigid, crystalline structure with ice here, right? And so that's going to be the least amount of entropy, very ordered, right? And we know that already because it's crystalline. Crystalline means ordered, okay? And then liquid water. Liquid water here, right? A little bit more space in between. So it's kind of in between with the entropy thing. But again, water vapor just floating around everywhere. That's going to be the most entropy right there, right? And then this is the example of a solid right here that is being solvated by water. So, remember that green and purple are sodium chloride, right? From the very beginning of the semester, we were talking about that. It was that video I showed you of Teo Gray making the popcorn, right? Or not making popcorn, but making salt forest popcorn, right? So the water is pulling off chloride ions and sodium ions into solution. So that's more energy, right? But if you take a look at this one here, though, right? If you take a look at this one here, this is a reaction. There's not a reaction arrow there. I guess you could consider that a reaction arrow, right? But you have 2 moles of oxygen, not oxygen, nitrogen monoxide. Nitrogen, isn't that nitric oxide? Nitric oxide? Whatever it is. So you have 2 moles of NO, right? And then you add it to 1 mole of oxygen, but then over here you have 2 moles of NO2, right? So what actually happened here is that you had 3 moles of gases over here, but over here you don't have 2 moles of gases. So in this reaction right here, did entropy increase or decrease? It did decrease, right? Because the less molecules you have, right, the less entropy you have, right? The more molecules there are, the more microstates there are, the more entropy you have, right? Makes sense? Okay. This takes us to the third law of thermodynamics, right? Where entropy of a pure crystalline substance at absolute zero is zero. And I've told you this before, it's impossible to get to absolute zero because absolute zero is like no molecular motion at all, right? Everything is moving. So even the table is vibrating. You just can't tell, right, with some molecular motion, right? But there's always a path for heat to travel. And so there's really no way to get down all the way to absolute zero there where there's no molecular motion at all, right? But consider that all atoms or molecules in perfect lattice are at 0 K, right? Or excuse me, 0 degrees Kelvin, right? There will be only one microstate, okay? So at 0 K, or 0 degrees Kelvin, right, the lattice is perfect. There is like no molecular movement at all, right? Which means if there's no molecular movement at all, and the lattice is perfect, and we're at absolute zero, right, there's only one movement, right, that a molecule can make, and that is staying still. Does that make sense? Right? At absolute zero, okay? So when you put it into Boltzmann equation here, right, and you do the ln of the microstates, right? You do the ln of the microstates. What is the ln of one microstate? It's zero, right? And then zero times the Boltzmann constant gives you what? Zero, right? And so that's why the entropy is what? Zero. Does that make sense? Right? So again, don't get confused again about the difference between a natural log and a log, right? Natural log is different from just a regular log, right? You can think of, if you didn't know this already, you can think of the natural log as being the one that has to be undone by E, right? Whereas the other log that we do is also known as log base 10. So you have to undo that with 10 to the something, right? Like when you do the pH and concentration calculations, right? So that's a good way to remember the difference. And don't confuse the two because you'll get you'll get the answer wrong. Okay? Because aren't you a lot of you in algebra right now, or in some kind of math class, aren't you? Pre-cal, yes. Huh? It does suck in the fact that this class would be easier, right, if you had done the math first, the pre-cal first. But that's okay. All right, so this is the next question. In which of the following cases does entropy increase in a system? Gases from either solids or liquids? Liquids or solutions from solids? The number of gas molecules increases during the chemical reaction. It's right before Christmas, Thanksgiving, so I'm making these super easy. So as easily as I possibly can make them, honestly. No trick questions here. All right. What's your guess? D, right? All of those are 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 reasons why entropy would increase in a system, right? That was right here. See? Gases form from either liquids or solids, liquids or solutions coming from solids, or um, the number of gas molecules increases during a reaction. That is okay. So now we introduce this thing called standard entropies, right? And so that means the standard entropy or the standard anything means the for example the entropy at standard temperature and pressure, okay, or even concentration, okay, and that's something you should have been introduced to in chapter 5, standard things, okay, standard state functions basically. And so if we know that the reference for entropy is 0K, right, which is absolute zero, the values for the elements are not 0K at standard temperature, okay? So standard molar enthalpy for gases is generally greater than those of liquids and solids. That makes sense. But you've got to be careful of the size. So the standard entropies will also increase with molar mass. As the molar mass increases, the standard entropy increases. Okay? And then also the standard entropies increase with the number of atoms in the formula, right? So that means there's more microstates. It makes sense, right? The more atoms you have, the more microstates you have. Okay? And so this is a list. And it's not a list you have to memorize or anything. It's just a chart that you can look up anywhere, right? You can see here, the first thing I want you to notice that when we have this here, this little S naught little symbol right there, that's always going to be, this little naught symbol will always indicate standard. So these are standard entropies, right? Or the entropies of these molecules at standard pressure and time? No, standard pressure and temperature, right? And so right? We have hydrogen gas here, right, which is much smaller than nitrogen gas. So notice that the standard entropy is bigger. Oxygen is way bigger than that, than nitrogen, a lot bigger there, right? Changes a little bit here with water, right? Because you have hydrogen in there too, but there's only 3 molecules there. Sorry, not 3 molecules. What is it? 3 atoms. 3 atoms there, but ammonia has 4 atoms, right? And that's why you get a larger entropy there, right? And then um, the how many is that? 4, 6, 6. Uh, I mean, you know, doesn't always work, right? Some exceptions, but the thing about it is, so just as a general rule, right? As the molecule gets bigger, or the more atoms there is, right? The more atoms there is, then the more atoms there is, the more standard entropy there will be. The higher the standard entropy, right? So that's the thing I want you to remember about this, right? Generally greater for liquids and solids. Oh, that's probably why. No, they're both gases. That's okay. So yeah, they're generally greater for liquids and solids, which makes sense. Entropies increase with molar mass, right? And then atoms, the number of atoms also makes it increase as well. Okay. And then so that's just a list you can look up in your book, if you had a textbook, but you can look it up online too, right? Table 19.1. It's a continued list here, right? So see, notice how solids here are all low. They're all less than 100, right? All these solids are less than 100. These solids that have more stuff added to them are bigger too, right? So that demonstrates part one of it all. Okay. So the next question is this: which of the following is not true of standard enthalpies? I'm sorry, entropies, not standard enthalpies, standard entropies, right? Standard entropy, the standard molar entropy for gases is generally greater for liquids than it is for solids. Standard entropies increases the molar mass, or standard entropies decrease with the number of atoms in a formula. Or none of the, is this say none of the above or all the above? Or all the above is true. So the answer here is what? C, yes. Standard entropies decrease with the number of atoms in a formula. That's wrong. It should be increase. So then how do you calculate the change in entropy? It's actually very similar to the way we calculate the change in enthalpy, right? You did the change in enthalpy in Gen Chem 1, right? It's almost the exact same equation, okay? It's going to be the change in the standard entropy equals the sum of the coefficients, right, or the number of moles of the products times the standard entropy of the products minus the sum of the coefficients of the reactants, right, or the number of moles of the reactants times the standard entropy of the reactants, right? So it's literally almost the exact same equation as you saw for change in enthalpy, right? But instead of seeing delta H there, what do you see instead? You see delta S, right? Instead of delta H, okay? So the thing here, don't get confused, right? N here and M here are both just the coefficients, right? Or the number of moles of either the products or the reactants, right? So it's like the sum, okay? So if you have more than one product, for example, it's a sum of those, right? Of those number of moles. Okay. So the next part here, I'm just going to tell you right now, is getting you to a very important equation. So don't freak out about the math. It's just me showing you how we get there. Okay. It's kind of like when we did kinetics and did all this like integration and and this calculus stuff, and it got you to the first order, second order, and zeroth order equations. Remember that, right? The integrated laws, right? It's the same thing, right? You don't need to know any of this stuff for a test, but except for the very last thing I show you up here. But I still want to show you how we get there. Okay, so heat flows, right, in and out of systems, and that changes the entropy of the surroundings, right? So for an isothermal process, an isothermal process just means so iso means same, right, and then thermal means temperature. Okay, and so the change in surroundings entropy, right, is equal to the Q. Q is the heat that's being transferred, right, from the surroundings over the temperature equals also the minus Q of the system, right, over temperature, okay? So remember in that picture I showed on Monday, if the system is losing energy, it goes to where? The surroundings, right? And if the surroundings is losing energy or heat, it's going where? Into the system, right? And so in the end, the change will always equal to the loss here or the gain here, right? Because it's all closed system. Make sense? Okay. So Q, remember, is the transfer of heat. Okay. So at constant pressure and a constant, and the isothermal, again, same temperature means constant temperature, right? And then constant pressure. The Q system is simply the change in the change in the enthalpy, standard enthalpy for the system, right? And so now you have this equation here at constant pressure, where the change in the surroundings enthalpy is equal to the minus change of the enthalpy of the system divided by temperature, right? Divided by temperature. Good stuff, okay? So that takes us to this equation here, which we talked about a second ago, not second, but Monday, right? The universe is composed of systems and surroundings. Everything is a system and a surrounding, right? So the change in entropy of the universe is equal to the change of the entropy of the system plus the entropy of the surroundings, right? The entropy of the surroundings, okay? So for spontaneous process, we've already made this clear, right? For the universe, the entropy, the change in entropy, right, is greater than zero for blah blah blah. For a spontaneous process, the change in entropy for the universe is greater than zero. Okay, it's greater than zero. All of that is to bring you to this point here. Okay, we have this equation that I just showed you in the last slide. We make a substitution for this right here, the entropy of the surroundings, with this, the delta H system divided by the temperature, which you saw 2 slides ago, right? And then we can multiply both sides by minus temperature, right, or negative temperature, right? Rearrange everything, and what that gives us is Gibbs free energy, okay? And now that's the important thing. Talking about Gibbs free energy, right? Where delta G equals delta H minus the temperature times delta S. That is the equation that you need to know right there, okay? Gibbs free energy, okay? Gibbs free energy. It's good stuff, very good stuff, okay? So what exactly does this mean? When you have this equation, right, I can on a test give you, a delta H or a delta S, or give you both, or give some stuff, and you have to figure out what the delta G is, and you have to tell me whether or not that delta G means that it's going to be a spontaneous reaction, an endothermic reaction, or blah, 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 all those other kind of stuff, right? Which I'll have for you, another you welcome moment in a second, okay? It's not going to be much it won't have much effect now, since you won't have to worry about it till like 2 weeks from now, but just know that it's there, right? Another you welcome chart, okay? Gibbs free energy, okay? Gibbs free energy says that if the delta G is negative, then the forward reaction is spontaneous, okay? If the delta G is zero, then the system is at equilibrium, right? And then if delta G is positive, the reaction is not spontaneous, but it is spontaneous in the reverse direction, okay? Oh no, dang it. Stupid chalkboard. Sorry. I got chalk on myself. Sorry. I ran into the chalkboard. I got chalk on myself. Okay, anyway, sorry. Back to this, right? So remember, delta G is negative. That means it's spontaneous in the forward direction, right? Delta G is zero. That's equilibrium. Delta G is positive. That's not spontaneous. And then when you look at reactions in like cell biology, in metabolism, and all kinds of health-related things, right? And all kinds of life-related things, these delta Gs are what tell you whether or not this reaction can happen on its own, or if it needs to have the help of an enzyme, okay? And you'll see that later, okay? So here we can see, for example, if you recall what Q is, right? Q is the reaction concentrations of the products and reactants at any time in the reaction, and the K is at equilibrium, right? And so, see, chemical equilibrium back to haunt us, isn't it? Right? So here we have pure nitrogen and pure hydrogen, right, as a gas, okay? Eventually, it's going to want to become, right, ammonia, no, not ammonia, yeah, ammonia, not ammonium, ammonia, right? And so notice that it's spontaneous to go to spontaneous to get to equilibrium, and from both the reactant side and the product side, right? It's going towards equilibrium here, spontaneous, going towards equilibrium here, spontaneous. So in the end, when Q equals K, which is the Q equals the equilibrium constant, the delta G equals 0. And what happens is that you have a mixture of both, interestingly enough, of both just hydrogen, nitrogen, and ammonia molecules. And that's actually the equilibrium, right? So after all this time, we were talking about what equilibrium really was, which is a reaction that gets to a point where it doesn't go completely to completion, and you have a mixture of it all. It all turns out it's because of the delta G is equal to 0. Is that crazy? Fun stuff, man. Fun stuff, right? So remember, right? We can start out here for the delta G, right, where it's spontaneous going towards the forward reaction, making going towards the forward reaction, making ammonia, right, when the delta G is negative, right? But this way it's going backwards, right? That's when the delta G is positive, right? And then here, this is delta G equals 0 at equilibrium. Make sense? Right? So I might, on the test, show you a graph like this of another reaction, and you'll have to label for me which side is the delta G side that's negative, which side the delta G side is positive, and which is the delta G is equal to 0, and all kinds of other fun stuff like that. Okay? It's fun stuff, right? Everybody should love thermodynamics. It's why it's why we're alive, right? It's why we live. It's great stuff. Okay. So here is your next question. A reaction is spontaneous in the forward direction if Gibbs free energy is which of the following? Anyway, so the answer to this is what? Negative, yes, because that is the form of delta G. That means that the reaction is spontaneous going in the forward direction. If it's positive, it's non-spontaneous going in the forward direction, but if it's spontaneous going in which direction? Reverse. Equal to 0 means what? Exactly. And is it a state function? It is a state function. This is actually one of our newest state functions, right? We've already talked about how pressure is a state function, temperature is a state function, entropy is a state function, enthalpy is a state function, and our friend and your friend Gibbs introduced to us a new state function known as delta G, right? It's great. It's great stuff. It's so great, okay? So great. So, just like any other state function, we can do this number here, well, except for temperature and pressure, but the other ones that have deltas in them, right? Uh, the same thing is true here, right? So this right here is called the standard delta G of formation, right? This is the standard delta G of formation. And so again, it's analogous to the other standard enthalpies, where we have the standard delta G, right? Right, is equal to the summation or the sum of the moles of the products times the delta G of formation of those products minus the moles of the reactants, the sum of the moles of the reactants, right, times the delta G of formation for the reactants, right? So it's the exact same formula as both the enthalpy and the entropy one, right, delta H and delta S, except now it's got delta G in it, right? And in the end, like I said before, delta G is what most chemists use to determine whether or not a reaction is going to be spontaneous or not, right? It's good stuff. And the reason why we do that is because remember this equation over here, right? Delta G takes into account what? Entropy and enthalpy, right? So since it takes into account both enthalpy and entropy, that's why as a quick look, a quick fix, we use that to determine whether a reaction is spontaneous or non-spontaneous in the forward direction, okay? So, right, so here's the thing I was talking about before, the standard states, right? So if it's a solid matter, right, if it's matter, sorry, the state of matter, if it's a solid, right, a pure solid would be its standard state, okay? And then if it's a liquid, it's got to be a pure liquid water, right? Standard for gases is at 1 atm, right? And then a standard for a solution is 1 molar, right? And then the element, if it's just an element, it's a standard delta G of formation at 0, right? So those are the standard states. I keep on talking about the state functions and the standard states, or the standard pressure and temperature. Those are it right there. Okay. So how does delta G, I guess I could have just gone forward instead of gone backwards there, but how does delta G change with temperature, right? So remember, right, if delta G is on the left side, right, and temperature is over here, since reactions are spontaneous, if delta G is less than zero, the sign of enthalpy and entropy and the magnitude of the temperature matters in spontaneity. You can't just say, like, since normally what I would say is, if the term is on one side and another term is on the other side, and none of them are in a fraction, right? Then if one goes up, the other goes up, right? Or but if it's where one term is on one side of the equation and the other term is on the other side of the equation, but it's under a division line in a fraction, then if one goes up, the other goes down. It's pretty easy to tell that way, right? So what this is telling you here is that temperature does matter, but you can't just say because it's on this side, delta G will up if temperature goes up, right? You can't just do that because you don't know what the delta S is going to be, and you don't know what the delta H is going to be, and also it's a negative term, okay? So this, my friends, is your welcome chart right here, okay? This is your welcome chart. And I promise that this will be much more apparent to how helpful it is to you when you're working on the assignment and then your next exam, okay? Okay, so notice here, right? We've got a negative delta H, a positive delta S, and then a negative T delta S, right? Which gives you an overall negative delta G, right? And when that happens, it's a spontaneous reaction in the forward direction at all temperatures. Okay? Does that make sense so far? Right? Okay. Okay. All right. So, for example, the example here is that we have two ozones, right? And these two ozones spontaneously become two oxygens or three oxygens, okay? So if delta H is positive and delta S is negative, and then negative T delta S, right, is positive, right? That will make the overall delta G positive, right? And that's going to be a non-spontaneous reaction at all temperatures, right? And so that would mean that oxygen doesn't spontaneously become ozone, which makes sense because we have oxygen in our atmosphere right now, right? 75%. No, that's not right. Nitrogen is 75%. Oxygen is 25% of our atmosphere, right? And if oxygen just spontaneously turned to ozone, we'd all suffocate, right? Does that make sense? It's crazy. It's just crazy stuff. And this is why. This is why, okay? So the thing that you need to notice here is the fact that you have a negative T, like a negative temperature, and depending on what the sign is, right, of delta S, right, which is over here, that gives you the overall sign of what? Negative T delta S. Does that make sense? Right? So if you have a positive delta S multiplied by a negative T, what do you get? A minus sign, right? You see that? Right? Here's delta S, it's positive. When you put it into this one right here, right? A positive times a negative T is what? A negative sign, okay? And then on this one here, delta S is negative, right? And you put that up there with negative T, a negative times a negative is what? A positive. And that's how you get a positive negative T minus negative T times delta S, right? So those are the two most important right there, right? These two, right? But then we get to the point here where if you have two negatives, right? A negative delta H and a negative delta S, right? That results in a positive negative, a positive negative, results from a positive, you get a positive from the negative T delta S. It turns out that it could be, delta G could be a positive or negative, right? But the thing to remember is this, okay? If it's two negatives, the delta H and the delta S are both negative, right? This is the only time it's like this, right? It's spontaneous at low temperatures, non-spontaneous at high temperatures. Okay? Makes sense? Right? So water here, right, goes to solid here, right? And if a water is going to solid, it's becoming ice. That means it's low temperature, right? And so that's spontaneous at low temperatures. Make sense? Okay? And then over here, if you have two positives, and this is the only time in this chart there's two positives, right? Only time in this chart that there's two positive, it's spontaneous at high temperatures and non-spontaneous at low temperatures, right? And so here we have solid water, ice, and it spontaneously becomes liquid water, right? And that means it's at a higher temperature, right? Spontaneous at high temperature, non-spontaneous at low temperatures. Okay? This chart is invaluable because I will give you so many like delta H's and delta S's and delta G's, and you have to tell me whether or not they're spontaneous, non-spontaneous, at high temperatures, at low temperatures, blah 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 blah. So, and this is just a very invaluable chart, right? You'll see how invaluable it is soon. Okay. Well, maybe after Thanksgiving you'll see how invaluable it is. So here's your next question. All right. Here's your next question. What reaction characteristics are indicative of a negative delta H, negative delta S, and a positive negative T delta S? Yes, that is correct. Spontaneous at low temperatures, non-spontaneous at high temperatures. Okay, but it won't be this easy on the exam. On the exam, it's going to have numbers. Okay, it's going to have numbers on the exam. Okay, so this is probably an equation I'll give you on the exam, right? One of the what I call the key equations. Okay, under any conditions, standard or non-standard, the free energy can be calculated this way. We can get the Gibbs free energy by getting the standard delta G, which is actually a literature value that you can look up, plus the ideal gas constant, plus the temperature, plus the ideal gas constant times the temperature, and then L and Q, right? L and Q. So under most standard conditions, right, which I showed you in that chart before, right, standard condition for molarity is what? 1 molar. You can say that Q equals 1. So what is the ln of 1? 0. So you can actually just drop that part right there, the L and Q part, right? And so now it's just going to be delta G equals the standard delta G the ideal gas constant times the temperature. Okay, so it's a super easy equation, but I'll put it on the test for you anyway. Okay, so remember at equilibrium, Q is equal to K, right? And so delta G is also equal to K. So what that means then is that 0 equals delta G, the standard delta G, plus the RT, L, and K. And if you rearrange those things, you get this guy here. So remember we went through all this crap, like the quadratic equation and dropping the X and all that mother in the chemical equilibrium section to figure out what K was? Remember that? Now you can just figure out K by doing the E2, the standard delta G divided by what? Negative standard delta G divided by what? RT. It's great, right? See, as you learn more and more chemistry, you see all these tools that we use to make things a little easier. You know? Why are you struggling? This is easy stuff. I mean, this is I literally I literally just distilled like 2 months worth of stuff. Oh, oh, okay, gotcha. Anyway, the point is, I just distilled 2 months worth of like chemical equilibrium, acid base equilibrium, and solution equilibrium to this here. All you need now to get K is e to the negative delta G standard divided by RT. Okay? I'll probably give you that on an exam. So the last thing we're going to talk about before we go into lab, right, is coupling reactions. And I alluded to this a second ago, right? I alluded to this a second ago, where very many biological reactions, and most of you are biochemistry majors that need to care about this. Yes, ma'am? So on the 8th, we don't have class. On the 8th? What is the 8th? So December, no, because we get out of yeah, the last day of class is that Monday. So the fourth test is December 6th, yes. And then the final is Tuesday, December 14th. Yes. And we have to come to campus what time? I have no idea. You have to look that up. I can't remember. It should be on the syllabus actually. So okay, so let me finish this lecture, please. There's only 2 slides left. Okay. So I alluded to this a second ago, and I said this a second ago where I was talking about how all biological, not all of them, but most biological reactions require are said to be spontaneous by chemists if they have a negative delta G, right? And so the way that the body does it, or cells do it, to make these things have negative delta G so that they are spontaneous, because normally they wouldn't be spontaneous, right? Is by coupling these reactions together and then using enzymes, okay? And so many natural processes would not occur alone, right? For example, glycolysis wouldn't occur alone. The TCA cycle would not occur alone. Electron transport, which is the formation of ATP, would not occur alone, right? Because forming an ATP from ADP and inorganic phosphate requires tons of energy. Well, how do you do it? You couple reactions together. Nature couples them to offer favorable energy conditions to cause something to occur, which is non-spontaneous alone. And if nature didn't do this, you would be dead, literally. Okay. So here's your example. Here's the example, right? Look at this is a super like dumbed down version of glycolysis, the TCA cycle, and electron transport chain, because it only shows the beginning and the end. Okay, it literally only shows the beginning and an end, right? And so here we have glucose, right? We consume some sugar, right? Which is actually kind of bad for you, but we consume some sugar, right? And it goes through this thing called glucose oxidation, right? In glycolysis, it gets broken apart because gluc means sugar, and then like glycolysis means to break apart. So it breaks apart the sugar, right? And then as it goes through and breaks apart that sugar, it oxidizes that sugar. So that's why it's called glucose oxidation. And the glucose oxidation happens, right, through, you don't see it here, but it's like glycolysis and the TCA cycle. And then right at this point right here, right, we have the TCA cycle is where carbon dioxide gets out, right? And this carbon dioxide literally is the carbon dioxide that you breathe out every single day. You know, much to the dismay of that FedEx employee that didn't believe me when I told her that we breathe out carbon dioxide. We do breathe out carbon dioxide. And the carbon dioxide you breathe out literally comes from sugar in the TCA cycle in the form right here, right? And then you go past that a little bit right around here or so, right around there is the electron transport chain, right? And that's what produces the water because the oxygen that you breathe in, right? Why do you need to breathe oxygen? Because you breathe it in so that you have oxygen in your electron transport chain to accept electrons, right? And when it accepts electrons, it becomes water, right? And that's why you have to breathe in oxygen. But it does all this to produce an ATP. It produces this ATP from ADP, right? So ADP is a low energy molecule, right? But you go through all these steps, a lot of steps. So there's 10 steps in glycolysis. Uh, I think there's also 10 steps in TCA cycle, maybe 8 steps in TCA cycle. There's like 4 complexes in electron transport chain, right? All these steps just to get breaking down glucose just to get a low energy molecule like ADP to become ATP, the high energy molecule, right? So quite literally, this process is using free energy released by oxidation in the form of glucose to convert ADP to ATP, right? But why does your body do that? Why do the cells in your body need to do that? Because it will take this ATP and the energy stored in it, because when you break a phosphate off of ATP, making ADP again, it releases tons of energy. Okay, and that energy can actually be used to turn simpler molecules, right, into bigger molecules that you'll use to make proteins, right? The structure of your body, or enzymes, right, that will carry out the reactions in your cells, right? So literally, the free energy released by ATP converts small molecules into more complex ones, big molecules, right? And so when it's a cellular development, cellular constituents, that means like organelles, right? Enzymes and stuff like that. So quite literally, if we didn't couple reactions in those, and this is like, wow, I mean, that's what, like 24 reactions maybe? Something like that, right? If you didn't couple all those together in that entire chain of metabolism, you wouldn't be able to get the glucose you needed to make CO2 and water, right? So that oxygen is the terminal electron acceptor to make this ATP. And if you didn't make this ATP to make smaller molecules, bigger molecules that make your proteins and your enzymes, right, to develop your cells, you would be dead, right? Does that make sense? Right? It's crazy. It's absolutely crazy. I'm sad to see that you're reacting to this the same way my other class reacted to this.
I wish that you could show this chart to my micro professor and have us do this instead of his teaching of the electron transport chain and TSA cycle.
TCA cycle? Well, no, I mean, if this were a biochemistry class, I would definitely go through every single step. Yes. But that's it though, right? Like you start out, if you didn't know this, right? And if you're in micro right now, you start out with a single glucose molecule, and at the end you end up with 32 ATPs, right? That one glucose molecule goes through glycolysis, the TCA cycle, which is known as the citric acid cycle, and then electron transport, right? And you come up with 32 ATPs from that. That comes from all the NADHs that are being made, right? The FADH2s that are being made, all that stuff, right? Does that make sense? It's great stuff, I think, anyway.
Are we gonna need sorry if you said this.
That's okay.
But we're going into the lab to do the period?
No, we're doing it here. Yeah, we're doing it here. All right, this is your last slide. In glucose metabolism, ATP is formed by coupling reactions to do what? Produce CO2 and H2O, convert more complex molecules into smaller molecules, or convert smaller molecules into more complex molecules, or all of the above. And this question quite literally is, right, what is the point of having an ATP? Why do we need ATP? Is it to produce CO2 and water? Is it to convert more complex molecules into smaller molecules? Or is it to convert smaller molecules into more complex molecules? I always get so excited when we start talking about biological systems in like biochemistry. And I wish we did more of it in Gen Chem, but we don't. So it's my favorite stuff. I said that about everything, don't I? I said that about chemical delivery. I said that about chemical kinetics too. How about this? My least favorite stuff is molecular orbitals. So molecular orbitals, that's my least favorite stuff. The stuff that we went over at the very beginning of the semester. All right, what's the answer here? Huh? It is C. In fact, it is C. ATP is used to convert smaller molecules into complex molecules, right?